Welcome to the Path. Partially autonomous trail hewer. Final presentation, FSE100, Fall 2023. Team 5, Funkworks. Team members, Dallen Blackham, Robert Dudley, Dustin Hayes, and Camden Caswell. Here's the problem. Since 2010, the market for construction has steadily increased and it continues to outpace the availability of skilled workers. We propose developing an automated solution that will decrease the cost and the time taken to lay brick pathways, freeing up skilled laborers to perform other, more important tasks. Currently, we're seeing a decline in the number of workers within the construction industry. Because of this, contractors are plagued with many delays because of a decreased workforce. So, many of these contractors are now turning to automation in order to meet their deadlines and save costs. How our product will add value. Automating the bricklaying process will decrease construction time and decrease the costs. The automation allows contractors to take on more jobs in spite of the labor shortage. Brick pathways are currently mostly laid by hand. The path system aims to free up time from just the most difficult parts of laying brick. The direct customers for our product would be contractors tasked with laying brick pathways, public works employees in a similar vein, and equipment rental businesses, as well as private consumers for the smaller units. Indirect customers would be federal, state, and local recreational area users, communities, and customers of private businesses. The design requirements for this product mean that it must be usable in a commercial as well as residential environment. It needs to be deployable by as few personnel as possible. It has to be durable to withstand heavy loads and dirty and rough environments. The design should not take much longer to lay a path than it would take a team of 2 workers. Additionally, the design must not cost significantly more than it would human workers. The design shall autonomously lay down a brick pathway once given a designated path by workers. The design shall prepare the path, level bricks, secure the bricks in place, and present a clean surface for the master bricklayer to finish. The swarm includes the ripper. It prepares the area for bricklaying by removing the turf. The bricklaying robot, bricked up, will lay down bricks within the path cut by the ripper. The brick leveling robot, it will level the bricks and secure the bricks in place using sand. The path cleaner will force more sand in between the bricks using roller brushes and will remove excess sand from the top using compressed air. Hello, my name is Robert Dudley. I'm the designer of the Ripper robot. The Ripper cuts a 1.2 meter wide path to a depth manually set by the operator. The operator also lays down a chalk line for the robot to follow. While following this line, the Ripper uses a milling cylinder underneath to grind up the turf, push it into a grading chute, and then expel it through an impeller out to the side. While the robot is moving, it's also laying down another chalk line behind it for the bricklaying robot to follow. Looking at the mechanical design, we have an ultrasonic distance sensor in the front as well as 2 IR line following modules. The motor systems include an impeller, a grinder, and 2 PMDC motors for the wheels. It has a centralized control system and a rugged, lightweight frame. In the rear, we can see the rechargeable battery port and a solar array, the chalk paint sprayer. It also comes with a positional discharge chute and 4 all-terrain tires. Looking at our circuit layout, we can see in the number 1 slot we have 2 PMDC motors to operate the wheels. Number 2 is our distance sensor that stops the motor when it comes within 20 inches of an object. Number 3 is the servo motor for operating the sprayer. Number 4 are the photoresistors in this diagram, which represent the IR modules which we'd use for line detection. Number 5 is a high-speed motor for impeller, and number 6 likewise is a high-speed motor for the mill. Number 7 is a solar collector. Looking at the Arduino code, we can see here we call in our libraries and declare our variables. We begin setup at this point, and further down here we loop through a series of statements to determine distance from any objects and whether or not the robot is still following the path. Then it will run one of a series of functions. Looking at the activity diagram, we can see what the functions do. After receiving a start command from the hub, it will turn on its front detectors, checking for distance and line alignment. If everything is good, it will start the impeller and grinder, then wait 2 seconds before moving forward while spraying chalk. If there's an issue that causes it to need to turn left or right based on where the line is, it will perform those functions in this area. If the robot detects something within 20 inches, it will issue a shutdown command shutting down all motors and alerting the hub of the problem. However, once it reaches the end, the operator will have sprayed a horizontal line which will trigger both detectors to a shutdown mode, telling the other robots in the hub that its job is complete and alerting the bricklayer that it can start. We've got a distance of 50, so we're good. Initializing startup, impeller came on, the grinder came on, and then the front wheels and sprayer came on. So we're going to go ahead and give it the emergency condition. So we're going to go ahead and say, oh, there's an object within 2 inches. Takes it a moment, problem detected, shutting down, sprayers off, motors are off, grinders off. The impeller does continue to run for a little bit, and that is to expel any material inside the unit. So let's go ahead and give it back up to speed. We'll go ahead and adjust this photoresistor over here. We're going to say, oh, I'm seeing a line. The left sensor has detected the line, and because of that, it's turning left. We see the high reading coming across here in the 600s. Go ahead and turn that back down, and we'll say, oh, now we've overcorrected. We've got a line detected on the right sensor. And there we go. We're getting over 600 on the right sensor. The cutoff for that is actually 500 in the code, and because of that, it is turning right. So I'm going to go ahead and put these back to normal. We'll initiate the shutdown complete sequence, the going home sequence. So I'm going to go ahead and set both of these to high, and then we should see it down here. Completing job. The sprayer is turned off. The grinder is turned off. It will continue running the impeller and the wheels. The wheels will run for about 5 seconds. The impeller will run for about 2 while it discharges any materials. Now, once this thing has moved, after 5 seconds, it'll go ahead and shut off those motors and tell you that the job is done, and it will just continue to update that status while sending a notice to the hub.
Hi, my name is Dustin Hayes. So today I would like to talk about the mechanical design of the robot. So first of all, you have these movement arms that position the bricks as they come down the brick chutes. The brick chutes are used to separate the bricks out and then allows us to actually better position the bricks whenever we are weaving them together for the brick path. We also have a bar where the distance sensor sits. It's this one right here. And that just measures how close the push bar is in the back gets to the brick chute. And then once it gets too close, the distance sensor will shut down the entire machine and it will allow the hub to receive an alert and the operator will have to come load it with more bricks. There's also low visibility cameras right here. This is how we actually trace the lines. And then you have the sloping apron, which allows the bricks to come down from the chute and lay down the path itself. Next, you have the servo motor right here and the hydraulic tank right here. Servo motor is what actually just operates a bar that moves these arms simultaneously back and forth. It's on a timer. And then you have a solid axle right here that is for just better stability, because on the inside of each of these wheels you have a DC motor which propels the machine, with all-terrain wheels just for better access to all types of job sites. And then back here for number 6, you have a spray nozzle that sprays white chalk for the leveling robot to follow next. So like I said, right here is the push bar. You have hydraulic cylinders that actually push it and then apply pressure for the bricks to be provided to the brick chutes. And then here's the distance sensor I was talking about earlier in this video. This in its entirety is the brick carrying platform, and that is mechanical design. So right here is my Arduino circuit. I'm going to start the simulation. So as my circuit is running, the servo motor is actuating back and forth between 360 and 300 degrees, while it also has a distance sensor that is measuring the pushboard distance to the sensor distance. There are 2 DC motors which will operate depending on whether it sees the white line or not. So I am using 2 photoresistors to simulate low visibility cameras. As you can see, they're both running now. And as one of the photoresistors no longer sees the white line, the associated motor will stop running. And then once it sees the white line again, it will run once more. The servo motor is also integrated with the distance sensor. So once the distance sensor reads less than 10 inches, it will stop operating, return to 0, as well as the wheels will also stop operating.
Hello, Camden Caswell with Team 5 Funkworks. Here is my robot, the Brick Compactor. You can see we have a 1.2 meter width roller in the front, a left and right hand IR sensor, and a ultrasonic distance sensor in the front, steering servo unit, Arduino, battery pack, and drive motors underneath. To the rear, we have a sand hopper here and a servo to control the feed door. For said hopper, we have our 1.2 meter width brush in the back, which is retractable via this servo unit. And we have our spray can with servo. Now, in addition to my FreeCAD model, I have, of course, a code and tinker here, which I will simulate. You can see we have two drive motors and our servos in the back here, our steering servo here, and we have our sensors in the front. Now, as you can see, we are currently moving forward and our steering servo is centered. Here are my functions here: forward, right hand turn, left hand turn, and stop. If the robot encounters an obstacle within 30 centimeters, it will stop, as you can see. And if we encounter a IR reflection, you can see that the servo will move to the 45-degree angle. And that's pretty much the functionality of it.
This is the path cleaner. After the brick leveling robot completes its task, the path cleaner will follow after sweeping as much sand as possible into the cracks and blowing the sand and remaining chalk off the sidewalk. On the top of it are two sets of solar panels to help power the robot during operation. On the back right, you can see some holes for the inlet for the air compressor to provide the air pressure for the air blowers. There are 4 wheels, 2 per side, and each wheel has its own individual DC motor attached to it. On the front is an HCSR04 distance sensor that is constantly detecting if there's any objects in front of the robot. Just below the distance sensor, there are 2 IR sensors that will detect the chalk path and ensure that it doesn't stray from the path. Working from left to right, underneath the robot, there's a servo that will actuate air to the air nozzles and secure air to the air nozzles when required. There are 2 sets of brushes. The forward brush will sweep the sand to the center, and then the second brush will sweep the sand to the edges in order to maximize the amount of sand that will fall in the cracks. There are 2 brush motors located underneath, as you can see, as well as the other right wheel motors and the right wheels. This figure shows the circuit design. There are 6 DC motors, 4 for the wheels and 2 for the brushes, a servo motor that will actuate air, a distance sensor to detect the distance objects are in front of the robot, and 2 photoresistors are substituted in for the IR sensors. This is the activity diagram for the path cleaner. Once the start signal is received, it's going to detect distance, and what the left and right IR sensors are detecting, either black or white. Depending on what is received, it will either stop moving, move forward, turn right or left, open the servo to allow air, secure the servo to secure air, spin the brushes, and then it will repeat the loop if the shutdown signal has not been received, or if the IR sensors are not detecting both white. This is the first portion of code. In it, we declare variables, assign the pins, and then get into the loop. It's going to check the distance, check what the left and right IR sensors are reading, and then it'll go into if and else if statements on what to do based on the activity diagram before. The second portion of code completes the activity diagram on the else if and else statements, and then it gets into the functions for check distance going forward and going backwards. This last portion of code includes the functions for turning left and right, blowing air and stopping air, stopping the wheels, turning the brush, and securing the brush, which is used in the if, else if statements before. This is a demonstration of the robot going straight. All 4 wheel motors are moving at the same speed, and the 2 brush motors are spinning, as well as the servo being open to allow airflow. This is a demonstration of when the distance sensor detects an object within 10 inches. As you can see, all motors have stopped and the servo is shut, securing airflow. This last demonstration shows the robot turning right when the right IR sensor detects white light. As you can see, the right motors are slowed down compared to the left motors, and the brush motors are still spinning.
Now we'll be discussing the collective behavior for the swarm. So every robot receives an initiation signal from the hub as the job is starting, and all of the robots will verify that they received the initiation signal. If not, then an alert will be sent to the hub. Next, the ripper will start up and it will inform the hub that it is started up, and it will commence working the job site. Once the ripper is done working the job site, it will then send a stop signal to the hub and then also send a startup signal to the hub and the bricklaying robot. The bricklaying robot will then commence laying a brick path after it is verified with the hub that it is sent the startup signal, and if it has not been received by the hub, then an alert will happen and you will have to start up the bricklaying robot from the central hub. As the bricklaying robot is laying the bricks, it will go through a series of tasks and verifying whether it has completed the task and if it has run out of bricks or not. If it has, the hub will be notified and then it will have to be reinitiated at the hub. Once it is finished, again, it will send a startup signal to the leveling robot, where the leveling robot will commence leveling all of the bricks. And same thing, if it runs out of sand, it will notify the hub, where someone will have to reload sand into it, and then you will have to reinitiate the leveling robot from the hub. Finally, after the bricks are leveled, it will send a startup signal to the path cleaning robot. Once the path cleaning robot receives that signal and is verified, then it will continue to clean the path and so on and so forth. Once it has completed the job, then it will send a complete signal to the hub, and then the program will stop running.
Shown below is the budget that would be needed for sensors and materials that would be required to manufacture our project. Each item has a price for each component, as well as the price to produce for all of the robots. Each component has a link to reference the price found for each part. Altogether, this adds up to roughly $6,000 just for materials alone. If labor is included to manufacture and quality inspect the robots, the price would be between $15,000 and $20,000. Currently on the market is a product called the Tigerstone Donging. This is a manually loaded brick layer that requires the workers to still manually place the bricks on the slope, and then the machine will guide them down into their placement on the ground. This does not level the earth, the bricks, or clean after the bricks. All those must still be done by workers, which leads to higher labor costs. Additionally, these cost $25,000 each, meaning our product would still be less expensive and require less manual input. Path is not only more affordable, but is more involved than any product that's on the market. Storm will prep the bricks, lay the bricks, level and support them, and clean the bricks all as one product. Investing in Path will save money and time for contractors across the nation.